Today we will solve the problem 4.22 of Griffith third edition Introduction to Quantum Mechanics, Chapter 4. The problem 4.22 consists of four parts. We will see it one by one. First part A is starting with the canonical commutation relation for position and momentum. Work out the following commutators. There are two set of commutators, that is totally six commutator. First we will take the first row, that is commutation of orbital angular momentum operator Lz with the xyz. First you take the first one, Lz with the x, computation of Lz with the x. Uh, by definition, we know Lz is equal to xpy minus ypx. This is by definition Lz. And x, we can split this into two commutation. That is first term xpy with the x. Here you have minus ypx with x. So now you can further you can expand these two commutation. First, you bring this right hand side operator, left hand side operator x to the left hand side, and pypx, and right hand side operator py to the right and xx. Similarly, here also y left side and px to the right side. Now we will solve one by one the commutator. The First, we will cancel these two. X will commute with the x. So this will become 0. And x and y, commutation of y with x also 0 because both are real numbers. So this will be 0. And what about the first one? That is commutation of py with the x. See, you can independently measure the x component and y component of momentum. So this also will be 0. And only thing left is minus one, y commutation of p with x. Commutation of p with the x is equal to minus iℏ cross. You know very well. If it is xp is plus x plus iℏ class, since px it is minus iℏ class. Already there is one minus here, so the minus of minus will become plus. So the commutation of Lz with x is equal to iℏ cross this y. Y will come here. So we have proved the first one of the row. In same method, you can do the next second one. And third one, obviously, you know that the angular z component of angular momentum will commute with z. So this will be 0 by simple logic. This is also 0. For second one, you can do the similar approach and you will get the result. Then we will move on to next section. So we have completed the first row. Then we will go for the second row. That is second row. First one is commutation of Lz with Px. So this Lz, as usual, this can be written as xpy by definition. This is xpy minus ypx. Now you can separate this into two commutation relation. First xpy with px, then minus, here you have minus, so minus I have taken out, ypx with px. Now use the commutation expansion, then the right hand side operator x become, sorry, left hand side operator x become left hand side, and right hand side py will become right hand side. Same, you expand this. Y will become to the left, and this px will become right. Here minus sign, so I have used negative sign. So I have expanded this commutation relation. Now we will solve one by one. See, it's very easily solve this. The y component of momentum is independent of x component of momentum. So you can measure both simultaneously. Hence, it will be zero. And same is here. You can see px will commute with px. This will become zero. The last one, the y will commit with x component of momentum because you can measure both independently. This y component will not affect the x component, momentum of x component. So this is also zero. So the only commutator left is xpx. The xpx is plus iℏ cross. iℏ cross. So ultimately, you will get only one term, iℏ cross py. So first one is we have proved. So in similar manner, you can prove the second one. And the third one, uh, you are taking z component of the angular momentum and z component of the linear momentum. Both will naturally commute. So you can easily say this is zero. This one is zero, third one. So we have completed the part A. We will move on to the next part P. Now the section P is use this relation, that is which we have proved already, these two, that is commutation of L with xyz and commutation of Lz with p x py pz. So use this relation and find out the prove that the commutation of Lz with Lx is equal to iℏ cross Ly. So now we are going to find the commutation of Lz with Lx. So you expand this Lx. Lx is because here you got x, then next is y, ypz minus zpy. So this can be expanded, useful expansion, and I can separate this into two commutation. That is Lz with ypz, Lz with ypz, and Lz with this one minus. That minus I am taking out. Lz with zpy. So now I can expand this in using commutator expansion. This y I am taking to the left hand side and this pz I am taking to the right hand side. So left hand side operated to the left, right hand side operated to the right. It's a usual commutator expansion. Same, you do the same thing here. Z left hand side, you bring that Z left hand side, and py right hand side, you take right. Now we have expanded. Use this result here. What is LZPZ here? This one. LZPZ is 0. You can see. So naturally, this is 0. Simply, you can take the angular momentum, nothing to do with linear momentum along the z axis. Both are the same axis, so this will be 0. Then what is LZY? You can see this one. LZY is iℏ cross x minus iℏ cross s. This is minus iℏ cross x. Then the third one is LZPY. What is LZPY? You can see LZPY is LZPY. Here you have LZPY is minus iℏ cross px. So this is minus iℏ cross px. Minus iℏ cross px. What about this? Naturally, Lz will commute with Lz. Lz with Z is equal to 0. This is also 0. Now only two term. Here first one is minus iℏ cross x. There is pz here, pz. Similarly here minus of minus will become plus, plus iℏ cross. You have z here and this is px, and this is minus 0, 0. So you take iℏ cross as common, you bring this positive parameter to first, that is zpx minus xpz. What is px uh, minus xpz? This one. What is this one? Remember that zx So naturally this will be Ly. Ly only you will get next x, zpx minus xpz. So this will become iℏ cross Ly. So iℏ cross Ly. So this is, we have proved this. Now we will move on to section C. Now we will move on to section C. Section C, find the commutators uh, Lz with R squared and Lz with P squared, where R squared is equal to x squared plus y squared plus z squared, and P squared is equal to px squared plus py squared plus pz squared. You can also use this relation which we have proved already. Then first one we will take Lz, commutation of Lz with R square. This can be written as x squared plus y squared plus z squared. So we have separated this into three commutators. Already we know that Lz commit with z, this is equal to 0. Third term will be 0. So don't worry about this. Then first two term you expand. Here you can take that as x. So you bring left hand x to the left hand side and right hand x to right hand side. Do the same thing here. Left hand y to the left hand side and right hand y to the right hand. This can be written as y into y. Now we will see one by one. What is Lz, commutation of Lz with x? You see here. Lz with x is equal to iℏ cross y. This is, sorry, this is iℏ cross y. iℏ cross y, this one. Same thing. Here it is iℏ cross y. Then what about the Lzy? You can see Lzy is minus iℏ cross. So this is minus iℏ cross. So this one will be minus iℏ cross. Minus iℏ cross x naturally. Then this one also minus iℏ cross x. Of course, minus iℏ cross. So now you can add both. iℏ cross, already there is x here, there is x here. You can interchange x, y back and forth because both are real numbers. So this first two term, if you add, you will get 2 times iℏ cross xy. This is xy and yx. Both are same. So same thing with this, which is equal to 2 times minus 2 times iℏ cross x y. Here you have y, here you have x. So if you add both, you will get 0. So this will be 0. Lz, commutation of Lz with R square, this one will be 0. Same thing here. You do the same thing for Lz with P squared. In a similar way, you will get Lz with p squared also will be 0. Now we will move on to the section D. Now, section D, so that the Hamiltonian H, which is equal to p squared over 2m plus v, commute with all three components of L, provided V depends only on R. Thus, H, L squared, and Lz are mutually compatible observables. So, in previous section C, we have seen that Lz will commute with both R squared and P squared. In similar manner, we can prove that Lx and Ly also commute with R squared and P squared. In turns, L commute with R squared and P squared. Here, now the question is whether L will commute with the Hamiltonian. Naturally, the first term of Hamiltonian is p squared. You forgot the constant term. So, L will commute with p squared. Only thing is we have to verify whether L will commute with V. First, for that, you take Lz. Lz, the commutation of Lz with R, which act on some arbitrary function. I have taken some arbitrary function f, which is a function of R. Then, by definition, Lz can be written as usual way, xpy minus ypx. So now you replace Py and Px in terms of its operator. Py is equal to minus iℏ cross uh, minus iℏ cross delta over delta y. Then Px also minus iℏ cross delta over delta x. I have replaced it by its operator. Then I can separate this into two minus iℏ cross here, minus iℏ cross x delta over delta y with r, this r, minus, already here there is one minus, minus of minus will become plus, plus iℏ cross y delta over delta x r, of course outside the commutator you have f. So now you expand this commutator, that is x delta r over delta y. That is your first, you are commutation of A with P is equal to AB PA. Then PA is RX delta over delta Y. Of course, you have F here. You do the same thing here. AB minus PA. AB is delta, sorry, Y delta R, P is A is Y delta over delta X, and P is R. Then minus PA. P is R, A is Y delta over delta X. Of course, you have F. Now you can uh, you can bring this into one form. You take iℏ cross minus iℏ cross as common. Then this iℏ cross you have taken away. So minus iℏ cross. So this will, first term will become minus. Then next term minus of minus will become plus. So I have made it plus, this term plus. So now we will simplify this term. Now we got this expression. What I'm going to do is you bring f inside. So the first term will become delta r f over delta y. Then here delta f over delta y. And here delta minus y delta r f. This f will come here over delta x. Same thing, the fourth term ry delta f over delta x. Now you differentiate this R F. First, you are going to differentiate R F, here one R F and here one R F. So you differentiate this term R F. Then what you will get is, first you keep R as it is. You take R away and differentiate F. Then you keep F as it is and differentiate R. you are keeping second term as it is. The third term, again, you are going to differentiate. First, you keep R as it is and differentiate F. Then you differentiate R and keep F as it is. Third term I am keeping as it is. Now you can see here this term, that is x r, here you have x r delta f over delta y. Similarly, here you can see uh, here x into r. You can see first and third term. You can see x r r x. Since that is a real number, you can interchange back and forth. Here x r uh, delta f over delta y. Here minus x r delta f over delta y. These two terms will get cancelled. Similarly, you can see here minus ry or whatever may be, both are same. This and this will get cancelled because this is minus and this one is plus. Um, Ultimately, only two term left. Here you have f, here you have f. You take f as a common. So then the first term will be x tr delta r over delta y. The next term is minus y delta r over delta x. We are taking f outside. Now we will reduce it further. So now we got this relation. Um, Now you can reduce this dr by dx. Dr by dx is equal to r. We know r is equal to x squared plus y squared plus z squared. Of course, square root of x squared plus y squared plus z squared. I am writing this as x squared plus y squared plus z squared power half. If you differentiate this, then you will bring this off here, then add and reduce this by 1. So that will become minus half. Then you differentiate with respect to x. Here you have x squared will become 2x. 2 will get cancelled. Then this will become x into x squared plus y squared plus z squared power minus half. So this can be written as x divided by the square root of x squared plus y squared plus z squared, which is equal to x by r. That's what I have written here. So Tr by Tx is equal to x by r. In similar way, Tr by Ty is equal to y by r. So here you replace this by y by r. This is y by r, and this one is x by r. It's the second term. I am replacing x into Tr by Ty is y by r minus y into Tr by Tx is equal to x by r. So here xy by r minus xy by r will become 0. This is 0. In a similar way, you can prove that uh, Lx commutation of Lx with R also equal to 0, Ly with R also equal to 0. That means L will commute with H, because we have already seen L will commute with P square, only term is V. If V depends only R, then that also will commute with L with H. So L commit with H. So all the three components were commit with each other. Thank you very much for watching my video and supporting me continuously. Thank you very much.